Let's wait for 2 3 minutes and then. So this is the eighth week. We have some extra session. So I'm writing it as week 8 problem solving session. And this is an extra session for the course mathematical methods. So in the last class we are discussing about the Laplace transform, and we have not yet seen how this Laplace transform can be used to solve the ordinary differential equations. So that we will see today. But before that, already in the last class, I was discussing about the inverse Laplace transform, and I have also listed some of the inverse Laplace transform. And based on that, I think yeah, one or two questions we have solved already for the inverse Laplace transform. And we will do some more. We'll see some more properties of the inverse Laplace transform, just as we have seen for the Laplace transform. So, similarly, for we will see it for the inverse Laplace transform, and we will try to develop our concept. So, today's plan will be to look at few more properties of inverse Laplace transform. We will see different properties as well as solve some questions. Then we will see how this Laplace transform and inverse Laplace transform, the entire thing, can be used to solve the ordinary differential equation, which I couldn't cover in the last lecture. Okay. The second one, is we will talk about Dirac delta function. We'll talk about the Dirac delta function, and we will also see what will be the Laplace transform of the Dirac delta and the Fourier transform, which is very, very easy based on the properties of the Dirac delta function. And the third one will be to look at the Green's function to solve inhomogeneous ODE. Right now, writing the ordinary differential equation that we will see today. So we'll solve some questions, of course, for the Green's function. Dirac delta, I have no question for that, but we'll discuss the concepts and just calculate the Laplace transform and inverse Fourier transform, or sorry, Fourier transform. And before that, we will discuss this part, which is of the week 7 content. Okay. So these are the few things which we will cover today. Okay, so before that, I have also already listed in the last class about the inverse Laplace transform list. So again, today also I wanted to show that the eight lists which I have given. So just I quickly write it and then we will start for different properties also for the Laplace transform. So these are the inverse Laplace transform, and these we can see it directly from the Laplace transform derivation which we have done in the last class. That is, we have seen that the Laplace transform of 1 is 1 by s. So if we take the inverse of 1 by s, it becomes 1. So in this way, we can write several others, like suppose 1 upon s to the power n, it will be t to the power n minus 1 upon n minus 1 factorial. Okay. Next, third one is an inverse 1 upon s minus a e to the power at. So the detailed derivation of the Laplace transform is being already covered in the last lecture. You can go to the YouTube link or the week 7 content. So there you will find these things. Okay. Further, so I'll not waste time. I just quickly write these things. S upon a square minus b square is cos hyperbolic sum e times t. The fifth one is suppose 1 upon a square minus a square and its inverse Laplace transform will require. So you get sine hyperbolic et, and couple of other things are there, like in the denominator if it is plus in between it becomes cos et. If you have in the numerator 1 and in the denominator is plus, sine between the a square and a square, it becomes sine at but divided by e. And the last one, which I have shown, is the inverse. This is the integration property 1 by s fs. We will discuss this 0 to t ft dt. Because in the Laplace transform part, we have seen that Laplace transform of 0 to 2 integration ft dt gives you fs by s, where fs is the Laplace transform of ft. Okay, so these are the few properties which directly comes from the derivation of the Laplace transform which we have seen earlier. Okay, so I will not go to the questions now because I have already covered it. So I will go to some few properties. So number one is, let's say it is saying that L inverse, that is inverse Laplace transform of S times Fs. Okay, that will be d dt, time derivative, first order derivative of the function ft plus some f of 0 into delta t. This also comes from the Laplace transform of the derivative of the function. We have seen that the Laplace transform of the derivative of the function is s times the Laplace transform of the function ft, that is f. Okay, we have already seen this. So just inverting it, we are getting something like this. Okay, we will solve the question for that, and let me through the question. This is find out the Laplace transform, or sorry, the inverse Laplace transform of this function f of s, which is given as a square upon a square plus a square. See, very clearly, if you look at the list, if you have this thing, s upon a square plus a square, we know that it is positive. Okay, but here extra s is multiplied in the numerator. So in this case, we can write in a different way. Say this f of s, which is being written here, can be written as s times some f dash n. This dash does not represent a derivative, but it is a new function f dash n. Okay, so I can write this s times s upon s square plus a square. Right? This we can write. So this one, this s upon a square plus a square can be written as f dash. All right. So this is fine. Now I need the Laplace inverse, that is inverse Laplace transform of f of s, which is nothing but L inverse of s times f dash s. And we know that what is the property says that it will be the time derivative of the f of t times sorry plus f of 0 times derivative. Fine. So f of t should be from this because if you look at this, remember this f of s. So L inverse of f of s is actually f of t. So in this case, when we are talking about this, s times whatever is there, its L inverse will be f of t. So we will try to see what will be the f of t. So f of t will be very clearly, if f dash s is this, the f of t will be cos of t times t. Simple. This is done. Now, what I require is d dt of f of t, right? D dt of f of t, which is nothing but there will be a which will be negative sign sine at, right? And also you have f of 0, which is nothing but cos 0 is cos of a times 0, which is nothing but 1, right? Cos of 0 is 1. Okay, and delta t is not required. It's a delta function, no doubt, but t is equal to 0. Let's for the time being, when it is multiplied by this, let it be 1 for the time being. Okay, so I am writing that f of 0 delta 0 is equal to 1. Okay, now based on all these findings, we can therefore write that L inverse of f of s, which is given, which we are writing as L inverse of s f dash s. And we have also seen that L inverse of f dash s is f of t. Then this can be written as your s times f dash s can be written as the time derivative of ft, which is minus e sin at plus f0 delta 0, which is 1. So this is the answer for the Laplace inverse transform, Laplace transform inverse or inverse Laplace transform of the f of s, which is given. Okay, so this is another way of uh, simplifying the inverse Laplace transform. Fine. So this is one of the questions I wanted to discuss. The next one, let me see. Yeah. So the second property is property number 2, which is, I think I have written it already. So this is f of s by s. This will be 0 to t L inverse f of s dt, which is nothing but L inverse f of s is f of t dt. That's all. Okay. So this is known, right? We have seen the Laplace transform in the earlier, in the last class. Laplace transform of this part is nothing but fs by s. So just let's take this inverse to get that. Okay. So we will solve the question for this also. Let me write it here only. Let us find out the Laplace transform inverse of 1 upon s plus 2. I'm giving a very simple example to illustrate this. You might get some complicated expression, but try to uh, take this 1 by s outside, or try to take it common, and then try to solve the other things. So clearly, whatever it is, let's say this is some f of s. So I can write the L inverse capital F s divided by what I am writing. So this is L inverse of f s. I'm writing it. I can write, of course. So L inverse can clearly see that f of s is nothing but 1 upon s plus 2 and times s. So capital F of s, I can write it as 1 upon s plus 2. Remember, property, look at the property. L inverse of fs by s is L inverse of fs dt 0 to t integral. So I have to only consider this. I don't need to consider fs by s together. Okay. So we will solve for the inverse Laplace transform of this and then integrate it. That's all. Okay. So what will be the inverse Laplace transform? ILT, let's say, inverse Laplace transform of 1 upon s plus 2. Very clearly, from go to your this one, let's say, see, I have 1 upon s plus something, right? S plus 2. But here it is s minus 2. So we can change the sign over here in the exponential. So you just go here and write down its inverse Laplace transform f of t will be equal to e to the power minus 2t. As you can see, there is a plus. If there is a minus, then you have to put it plus. Okay, so right now it is e to the power minus 2 as per the inverse Laplace transform of the function. Then this is done, but what I need is L inverse of fs by s. For that, what we need to do is we have to take an integration of the function which we have got. That's all. So what will be the integration? E to the power minus 2t divided by minus 2 from 0 to t. So it will be e to the power minus 2t by minus 2 minus minus will be plus and put it 0 over here. So it will be half. So it comes out to be 1 minus e to the power minus 2t divided by 2. This is the answer for the question. Okay. So what we have seen so far is you have s times fs. You can do it operator means it's a differentiation of the function has to be found out. When you have fs divided by s, when it's the Laplace, I would say transform function s. If that is divided, then you have to integrate the function. These are the two differences, and we have seen it in the Laplace transform also, exactly in the opposite way. Okay, the third property of inverse Laplace transform is the shifting property, just like we have seen it in the Laplace transform. So this is the shifting property. Okay, so what is this shifting property? Is that you have suppose L inverse of f of s, which is f of t. This we generally write because Laplace transform of f of t is f of s. We generally give this kind of a symbol. Now, L inverse of, if I write f of s plus a, let's say, then what will be your corresponding time function? It will be nothing but e to the power minus 18 L inverse f of s. This is exactly similar to the what you call the shifting property of the Laplace transform. But since we are doing the inverse Laplace transform, we are taking the L inverse of this. Okay, so this is how the uh, the shifting property looks like. So if anyway you see I will give a question definitely. So if you see that something is added to S, because here we are talking about the inverse Laplace transform. So for inverse Laplace transform, your function will be only in S. So whenever you see some constant is being added or subtracted from S, then you can use this kind of a shifting property. For example, let us take a question and try to solve it. Say let us find out L inverse of S upon S plus 3 whole square plus 4. So you can clearly see that you have an S plus 3 over here, correct? So we can try to see that how we can solve this particular part. Okay. So now, very clearly, you have f of s plus a, right? Now, but what can we write about the f of s from here? So simple is that you will not have this s plus a part, right? So it will be something like this. So f of s can be written as, or just a minute, let me show one more thing. Look at this. This is somewhat a complicated part. Can we write this as L inverse of s times 1 upon s plus 3 whole square plus 4? This we can write. So it is something like s times fs, right? So I'm writing it like this. So s times some fs. Okay. So what we do is that f of s is nothing but 1 upon s plus 3 whole square plus 4. Okay. So this is what we have got. Okay. Now I know that 1 upon s square plus 4, if it is there, let's say, then we can write this as 1 upon 2 sine of 2 times 2. This we can write clearly. But here it is s plus 3 whole square. That means something is added to the s. And what is added? Take constant b. Okay. Then just keep everything same. Let it be 1 by 2 sine 2t. Okay. Why am I writing 2? Because it is 2 square. Okay. 4 is 2 square. So I need to have 2. Fine. So 1 by 2 sine 2t we have for this. But along with that, because of this shifting property, that there is a s plus 3 here, you have to multiply an exponential with a minus 3t. Because if you look at the thing, if it is plus, then here is a minus. So I am writing it like this. Okay. If this is what we have got, now you have s times fs, right? If you have s times fs, then if you know your f of t, that is inverse Laplace transform of fs, you know. Now what you have to do is that you just have to, so L inverse of capital Fs, so s times fs is nothing but d dt of ft, and plus of course f0 you can put. Fine. So this, okay. Now if you put t is equal to 0, this will be 0 only, right? So this is gone. If you just put 0 here, sine 0 is 0, so it is gone. You only have to differentiate d dt of ft. That's all. So you can try it, or I just put it here. So d dt of half sine 2t e to the power minus 3. Okay, so half you can take outside. First, you, let's say, differentiate this sine 2t. It will be 2 cos 2t e to the power minus 3t, and plus sine 2t as it is, and it will be minus 3 e to the power minus 3. All right, so you can keep half, it doesn't matter. So you have 2 cos 2t e to the power minus 3t minus 3 e to the power minus 3t sine 2t. So what finally we are getting is that, let's say, okay, let us take 2 inside, and we get e to the power minus 3t can be taken common, of course. This becomes cos 2t minus 3 by 2 sine 2. That's all. So this is what you will get as an answer. Okay. One more thing you can do is that in this, you add a plus 3, you subtract a minus 3. Okay. This also you can do. This is also a fine way of doing it. You add plus 3 and subtract minus 3. So this is another approach. So for the same question, so any way you can do. So just the way you have to perceive it. Okay. So for the same way, for the same, I'm sorry, for the same question, we can also do this. Also do, say, what is being given? So s upon s plus 3 whole square plus 2 square or 4 is there. I can do what is that s plus 3 upon the same thing denominator, s plus 3 whole square plus 4 minus 3 upon s plus p whole square plus 4. Alright, this also we can do. And you know the Laplace transform of, we know the Laplace transform of this, we know the Laplace transform of this. Simple. See, this is corresponding to s upon a square plus 2 square, which is cos. But cos which is shifted. So it will be cos what 2t e to the power minus 3t. Okay. But here what it will be? It will be just minus 3. And you have to, what you have to do is that you have to, I will show you. This one can be written as 1 upon a square plus 2 square. Okay. So what I will do is that the second part minus 3 is there. I divide by 2. I also multiply by 2. So 2 upon s plus 3 whole square plus 2 square. Now look at this. This is corresponding to the signs. So it will be minus 3 by 2 sine 2t, but it is shifted to e to the power minus 3. So clearly, we are getting the same result. So in this way, you can proceed, or otherwise, you can try to use the S of fs. Whatever way is fine. Okay. So this is how you can also approach the question. Fine. What else you can do? Okay. There is another, say, property. The fourth one is that you take the inverse Laplace transform in, suppose, Laplace transform of the derivative. Okay, so you have L inverse dds of f of s, which is nothing but minus p L inverse f of s. Okay, and this can be written as minus p f of t, because f of s, its inverse Laplace transform is f of t. This is how we define. Okay, so this is another property, and this comes from a very similar property of the Laplace transform of t to the power n ft. If you just go to the week 7 content one, you will get t to the power n f of t. We have solved how to do the Laplace transform. Exactly the opposite way is the inverse Laplace transform. So this is also very known part. Okay, so we will try to see that how we can uh, take up a question and try to solve it. Okay, so let's see the question, which is L inverse s upon a square plus a square whole square. Okay, so this is your f of s. All right, but what I'm saying is that let us not take this as your f of s. Let us not take this as the f of s. Rather, let's do it like this. Let's say dds of f of s is, let's say this, minus, I'm just writing it. You will understand what I'm trying to say. See, dds of f of s is suppose this, okay? Or yeah, so this is fine. This is not the dds of f of s. I just wrongly showing it. I'm saying that let us say that f of s is this. Let f of s is this. Now, why am I writing it? You will understand. If I take dds of f of s, then what it will be? It will be nothing but s upon a square plus a square whole square. You can try. See, 1 upon a square plus a square, you have to differentiate with respect to s. So you take it in the take the inverse of this and take the derivative. You get 1 upon a square plus a square whole square, and in between in the bracket you have an s square. So there will be 2s. The 2 and 2 will cancel, and you get this. Okay. So if we take f of s as this, you will get this. Now then why am I suddenly picking up f of s is some arbitrary function? No, I'm not picking up an arbitrary function. I am trying to reduce this part by integrating to this. And integration means you don't need to formally solve the integration. Just apply your mind and try to reduce into a function which will be, when get differentiated, you get this. Okay, so you can easily see that this will be the function. Okay, so this is my intuitive function. Okay, I have prepared it, and it is very easy to prepare. Either you integrate it, fine, that is absolutely fine. This is a mathematical formal way, but you can also just try to think and write the function. Okay, that this should be the function. When I differentiate, I will get this, which is in the bracket. Okay, so DDS of FFS is this. So can I now write that L inverse of DDS of f of s is nothing but L inverse s upon s square plus a square whole square. This now I can write because I have got it. Now, for this to write, if I write like this, then my f of x will be what? Which I have written. That is minus 1 upon 2 times a square plus a square. Alright, this is fine. But I need to find out f of t for this. Correct? Why? Because I need it here. And then I have to just multiply by t. That's all. Right? So what will be the f of t? Great, let's see. So it will be nothing but L inverse of f of x, which will be what? Very simple. See, f of s is minus half 1 upon a square plus a square. And we know that 1 upon a square plus a square is something related to sines. So minus half 1 by a sine a. This is already listed in the formula. You will see it. So minus 1 upon 2a sine at. Alright, so this is what you will get. Now, L inverse of DTS of Fs is what I need to find out, is given in the question. That can be written as minus t times minus 1 by 2a sine a. Alright, so this becomes t by 2a sine at. That is the. Alright, so this is how you can try to solve the question. So instead of directly writing this as your f of s, try to look for certain properties and try to visualize based on that. So it will be easier for you to solve. Okay. I know every properties are not easy to remember, but if you just remember the Laplace transform properties, it will be very easy for you to reproduce the inverse Laplace transform properties and try to implement it. Okay. So this is another. Let me give you another property which you want if you can use, otherwise you can leave it. Whatever way is suitable for anyone who is using this Laplace transform, you do it like that. Okay, f of s ds. Suppose the Laplace transform inverse or inverse Laplace transform of 0 to infinity fs ds. This I need to find. Then what you have to do is that you just have to write f of t by t. And what is this f of t? Very simple. This is nothing but 1 by t and L inverse of f of x. That's all. Okay, this is the property. I'll give a question and illustrate that how we can use this. So L inverse of, let's say it is given that 2s divided by s square plus 1 whole square. This you have to uh, find out. Then, okay, so if this is what you have to find out, then what you can do is that you see that you can reduce this to something like t times L inverse of, say, 0 to infinity 2s upon s plus 1 whole square ds. Okay, why am I writing PL inverse? Based on the previous property. See, what I'm doing is that instead of writing this as the original f of s, it is somewhat complicated, no doubt about this. So if instead of writing this as fs, I'm writing this as dds of fs, which is nothing but t times L inverse of the integration of this, right? Because what we have done in the last question, was also integration. This is also came from integration of the original function, right? The same thing we are doing here, okay? And multiply with the t because that is how the formulation was written, and try to solve this. When we try to solve this, so we get t times L inverse of, and this you can solve with integral, and you can reduce this to s square plus 1 to infinity dy by y. We just try to solve it later, it doesn't matter. This is not very important property to use, minus t, uh, 1 by y from s plus 1 to infinity, and this gives you t times L inverse of 1 upon s square plus 1. And once you get this, you know that this is nothing but t times sine c. This is somewhat complicated. You don't need to focus so much on this. Rather, I can say that your L inverse of f of s is actually t L inverse 0 to infinity or s to infinity f of s is. I think it is not very important, so you can leave this part because this is somewhat a way of complicating the things. So let us leave this part and let's go to solving the another question and the way of solving the Laplace inverse Laplace transform. Okay, so let us say one last question before going to how to solve the ordinary differential equation. Another interesting way to solve the inverse Laplace transform is say this Ts plus 1 divided by s minus 1 s square plus 1. Okay, suppose this is the question which is given. So you have so many properties, suddenly you feel that it is very confused to solve this kind of a question. The best way is that you use the the partial fraction kind of a method. So what is that? What I do is that I am writing Ps plus 1. This is the easiest way of doing anything. So this is s minus 1 and there is an s square plus 1. What you can do is that you can write e times s minus 1. And since there is an a square over here, I will write bs plus c divided by a square plus 1. Whenever you have a square, you have to write in the numerator like this, b times s plus c. Whenever you have a simple function like this, s to the power 1 minus something or s, you have to write only a constant. Okay. Now you try to solve whatever way you want it to. So you write it s minus 1, s square plus 1. Aim is to find out a, b, and c. That's all. So s minus 1 means it will be a s square plus a. All right. Plus bs plus c times s minus 1. Right. This is how you do the LCM and do the sums. Finally, you get a is square plus e. Now I will multiply these two. So it will give you bs square minus bs plus cs minus c divided by the same s minus 1 s square plus 1. All right. So now you have a plus b s square plus minus b plus c times s. This one, these two. And finally the constant a minus c. And in the denominator, you have the same s minus 1 s square plus 1. And on the left hand side, you have 3s plus 1 divided by same s minus 1 s square plus 1. Just now you have to compare. Okay, so s minus 1 square plus 1 can be gone. Now you have to compare both sides. So I can clearly see that a plus b, because it's a term which is a coefficient of s square and which is not present here, so a plus b will be 0. Minus b plus c will be equal to 3. A minus c is equal to 1. Alright, these are the three equations we have. And now we can easily solve. One is that a is equal to minus b. Okay, next, what we can do, we can solve these two, right? How? Minus b plus c is equal to 3. A is minus b minus c is equal to 1. So just Chop this one out. So it will be minus 2b is equal to 4. B will be equal to minus 2. Done. If b is equal to minus 3, then a will be what? 2. If we have done this, just put it in any of the equation. Let's say a minus c is equal to 1. So it will be 2 minus c is equal to 1. So c will be equal to 1. Okay. So these are the couple of things which we have got. Therefore, we can write L inverse of 3s plus 1 upon s minus 1 square plus 1 can be written as A. A is 2 upon s minus 1. This is one part. Second part is minus 2s plus 1 divided by s square plus 1. Now, what thing has improved? You can see that there are two prominent summations, right? One is 2 upon s minus 1, another is something related to s square plus 1. Once we have reduced to this, it is easy to solve, right? So, what we will do is that we will do some more justification, not justification, we will try to solve more. 2 upon s minus 1. Okay, then minus 2 s upon s square plus 1. Look, we have reduced it into the cos form or sine form plus 1 upon s square plus 1. The last one, Laplace inverse, you will easily get. I think every term you can get the Laplace inverse very easily. How? Now this is say 1 upon s minus 1. So 2 times L inverse of 1 upon s minus 1. Easy to find out. Next, minus 2 L inverse of s upon s square plus 1. Very easy. Cos, okay, plus 1 upon, sorry, L inverse of 1 upon s square plus 1. This is sine. That's all. So 2 into this will be e to the power t because constant is 1. Fine. Next, minus 2. This is cos t. Already told you. This is sine. That's all. This is the answer. So, whenever you have some complicated expressions, immediately don't think about the property. Just see that can you reduce this to some partial fraction kind of a thing or not, based on this way, the way I have solved. And then compare the coefficients, try to reduce it into some known forms. See, these are the known forms, and based on that, you can easily calculate the inverse Laplace transform. So, the basic thing which I think when I did the Laplace transform, inverse Laplace transform, is that one thing that is you should know these properties. These 8 properties you should know. Okay, these 8 9 properties, whatever I have written, this you should know. Based on this, whatever the question comes, you try to reduce into those forms. Once you reduce into those forms, remember these 8 9 properties and try to put and calculate the inverse Laplace. Okay, so this is the main I would say trick for solving all the Laplace transform questions. And I have solved many questions so far, so that will be easier. Okay, fine. The next one is how to solve ODE using Laplace transform. So ODE solving. I have some 2 questions that will be easy. ODE solving using Laplace transform. Okay, so let's directly jump into a question and try to solve. Okay, that will be easy. So let us take a differential equation. Y double dash plus 25y is equal to 10 cos 5t. Looking into this particular question, you are absolutely sure that it is an inhomogeneous differential equation. So we don't need to look at now whether it is a homogeneous equation or inhomogeneous equation. Because earlier we were saying that for the homogeneous equation, we only need the complementary function, the 2 independent functions, and then we go for particular solution. Here you don't need anything. Only one step, we will go to the solution. Okay. So along with that, some conditions were given that y of 0 at t is equal to 0, y is 2. And the first order derivative of y, it's 0 to 0. Okay. So what I will do is that we will apply Lap- Laplace transform on both sides. Okay, you apply Laplace transform on both sides. So okay, fine. So what will be the Laplace transform of y double dash? I have told already in the last class that it is important. So you must know it should be a square Laplace transform of y minus s of y of 0 minus y dash of 0. Okay. What is Laplace transform of y dash? This these two things at least you should know. So s times L of y, Laplace transform of y minus y of 0. That's all. Okay. These two things one must know. Okay. Fine. Otherwise everything is fine. Very interesting to see that there is no y dash term here. So we will only use this L y dash, y double dash. So applying Laplace transform. Okay. So what you will get y double dash plus what is there in the question 25y. And on the other side, you have Laplace transform of 10 cos 5t. Okay. So take the Laplace transform of y double dash. So what it will be? A square L of y, Laplace transform of y. Okay. Then what? Then plus 25 L of y. But wait, these terms are also going to be there. Minus a. What is y of 0? Given as 2, I think. So 2. And what is minus y dash of 0? Is 0. What is the Laplace transform of 10 cos 5t? 10 will be coming outside. Cos 5t will be s divided by s square plus 25. Right? 5 square, 25. Okay. This you should know. The Laplace transforms of individual functions you should know. Once we have done this, just we can write s square plus 25 L of y, okay, minus 2s is equal to 10s upon a square plus 25. All right. Next step, keep the L of y, Laplace transform of y as it is on the left hand side and take every other term on the right hand side. So you get 2s upon a square plus 25, okay, plus 10s divided by a square plus 25 whole square. Okay, this is done. Next thing is what? You have to take inverse Laplace transform, both sides. Transform both sides. Clearly, you can see if you take inverse Laplace transform on both sides, here you will get only y, and then this side, whatever you get is the result. That's all. This is what the simplicity of the Laplace transform using Laplace transform to solve ordinary differential equations. So we will do that. So on the left hand side, it will be y only because L inverse L of y is y. On the other side, you have L inverse of two functions, 2s upon s square plus 25. The first function is easy to find out. Second function, we will see 10s divided by s square plus 25. This is also easy. This is also easy. We have to think it. Okay. So this will be y. And what about this? 2s upon s square plus 25. So 2 can be taken outside. This is nothing but cos of 5t. Right? Because it is s square plus 5 square, 25. Plus L inverse of, let it be as it is like this, 10s upon a square plus 25 whole square. Whenever you see that anything like in the denominator, it has a square, try to reduce it by integrating it. So how will I do this is that, see, a square plus 25 is there. If I write a square plus 25 in the denominator and put a 1 here, to take its differentiation, what it will be? It will be minus a square plus 25 minus 2 into 2s. Right? This is what you will get. And exactly what you require. 2s upon a square plus 25 whole square with a minus sign. Is this seems very clearly? So if I put 1 upon a square plus 25 with a negative sign, then this will go minus minus will be plus. It will go. It will be like this. Okay. And if I just put a 2 here, then you will get a 2 here also. So that will also go. So you get s upon s square plus 25 whole square. Right? And a 10 is there, 10 I can take outside. So what I am getting is that 2 cos 5t plus 10 L inverse of, can I write now this as BDS of some f of s? Well, what is this f of s? Is what we have derived so far is minus 1 by 2 a square plus 25. Okay, so this we have tried to see. Fine. I think this is all right. Now, what else we can see is that, yeah, this is fine. Okay. So now, what we can look into this is that the DDS of f of s we have reduced to already. So we know that DDS of fs, if you take its Laplace inverse, then what you get is minus t times L inverse of ft, or oh, sorry, f of the small f. Okay, this is what is the property which shows. And what is this? L inverse of fs is what? Is simply minus 1 by 2 is, as it is, leave it like that. And there is a 5 square here. So multiply by 5 and this will be sine 5. That's all. So what you get is minus 1 by 10 sine 5. Okay. And let me just quickly see that whether it is t or minus t. I just need to. Okay, it is minus t. So it's fine. Therefore, L inverse of what you have DDS of f of s is nothing but t by 10 sine phi. And what you already have outside is 10. So y will be equal to 2 cos 5t plus t sine 5t. This is what we get. Okay, so this is how you have to solve. Okay, fine. Yeah. Just let me check the calculation once again. Yeah, this looks fine. Hmm. Just a minute. We'll solve few more questions and then go for the Dirac delta function. Okay. The next, let us take another question. Okay. Let's take a very simple question first and then take another. And so we will solve now two questions quickly, and then we will complete this section of the Laplace transform and inverse Laplace transform and solving the ODE using the Laplace and inverse Laplace transform. This part will be over. Then we will go for a direct delta function and try to calculate certain things. Then we will go for the week 8 content actually, that is the Green's function, and we'll try to solve some question based on that. Once we finish this, in this week. The next Tuesday, 6 to 8, whatever the session will be, there I will try to show the Corbinius method, the power series solution to solve the ordinary differential equation. And we will end the course. Fine. So let's take another question. So you have y double dash plus y equals 0. And it is given that y of 0 is 1, y dash of 0 is also but minus 1. Okay. So just put the Laplace transform, apply Laplace transform both sides. This is a homogeneous equation, does not matter. So s square L of 1 plus, oh, okay, minus s of y of 0. Let us write all these things. Y dash of 0 plus y, so L of y is equal to L of 0, which is nothing. Okay, fine. So the next step will be, so s square plus 1 L of y, and what about this? Minus s plus 1 is equal to 0. Y dash of 0 is minus 1. That's why I'm writing plus 1. So this becomes L of y, which is nothing but 1 minus 1 plus s divided by s square plus 1. So L of y gives you s upon s square plus 1 minus 1 upon s square plus 1. Easy to solve. You take the inverse Laplace transform. So INT, okay, inverse Laplace transform. So you get y. This will be L inverse of s upon s square plus 1 and minus L inverse of 1 upon s square plus 1. Both are very easy to solve. This is nothing but cos t minus this is nothing but sin t. That's all. This is the answer. Okay, very easy question. Let's go for the last question for this OD solving, and then we can uh, shift to the Dirac delta function. Okay, so the next question is y double dash plus 2y dash plus 5y is equal to 0. Okay, another homogeneous equation with y of 0 is 2, y dash of 0 is minus 4. Okay, so let's try this one. So apply Laplace transform both sides. So right hand side will be 0, left hand side only will be the transform will be applied. So it will be s square L of y as we have done in the earlier case also. S y of 0. First I write, let me write, and then we put the values. 2 of L of, sorry, S times L of y minus 2 times y of 0, right? And then you have 5 times L of y, which is equal to 0. Okay, so this is what you will have. So finally you get the values s square, uh, where is L of y are there? So this plus 2s plus 5 L of y, this I take common, minus s times y of 0. Y of 0 is 2. So 2s. Y dash of 0 is minus 4. So plus 4. Minus 2 of y0 is 4. Right? 2 into 2, 4. Yes. So this is equal to 0. 4, 4 cancels out. So L of y gives you 2s divided by s square plus 2s plus 25. This is what I'm getting. Right? Yeah. Yeah, I think. Okay, this is what I'm getting. So what we can do is that, can we convert this into a perfect square kind of a thing and then try to look for anything else? So let's take the denominator s square plus 2s plus 25. It can be written as s whole square plus 2 times s into 1 plus 1 square, okay, minus 1 square plus 25. Okay, we can write like this. So we get s plus 1 whole square plus 24. All right, so we get something like 24. Okay, so fine. So what you get is that n of y is nothing but 2s divided by s plus 1 whole square. Okay, just something. So this is 5. 2s plus 5. Right? So this is 5. So this will be plus 5. So 5 minus 4 is 1 is 4. Okay, 5 minus 1 is 4. So this plus 2 square you can write. Now it's easy. So y will be what? L inverse of 2s upon s plus 1 whole square plus 4. Okay. Don't arbitrarily use that. See, I have something like s upon s plus s square plus 4 and write the cos. Okay. Don't do it very. So do anything whichever you are doing very carefully. See, you have an s plus 1 over here. So you have to reproduce here s plus 1. Remember. So instead of just quickly writing it, 2 you can take outside, it's fine. You add plus 1, you subtract minus 1. I have shown this earlier also. And then solve. That is the correct method. Okay. So 2 L inverse. Let's take this s plus 1 upon s plus 1 whole square plus 2 square. Okay, this is number 1. Number 2 is that minus 2 L inverse 1 upon s plus 1 whole square plus 2 square. Then y becomes 2 times now s upon s square plus 2 square. So it will be cos definitely 2t. Okay, but along with that there is a shifting. So e to the power minus 2 minus 2 times this will be sin 2t, but again e to the power minus 2 because there is a shifting property which is coming into picture. So it will be e to the power minus t with a 2, and you have cos 2t minus sin 2t. That's all. This is the answer. Okay, so this is the final answer which you get. Very important. This part, again, this is very important part. After this, many people can do some mistakes. Okay, so this is the way you should proceed. Okay, so we have solved 33 questions for the ordinary differential equation using Laplace transform. Now, this is, I think, this part is over. The Laplace transform part is over. Now we will go to another interesting topic, which is nothing but the Dirac delta function. So, not take much time. Dirac delta is it's a small concept, and some properties will be there, and I will show some more things, and then we will go for Green's function. Will not give much details about the Green's function because you can see in the notes which are there, the lecture notes, as well as the videos which are already there. But I will show that how to solve certain questions. Of course, I will take it from the notes, some parts, but mostly we will solve some questions, how to use the Green's function and to solve for the ordinary differential equations. That will be one of the important parts. Okay, so let's go for first the Dirac delta function. Because you will see that in the Green's function also this impulse of Dirac delta function is very widely used. Okay, so what is the mathematical definition of the Dirac delta function is that it is represented as this delta x minus a. This is equal to 0 and this is equal to infinity I cannot say it is equal to infinity, it should tend to infinity. 0 when x is not equal to a, and infinity only when x equal to a. So theoretically, this function goes to or tends to infinity. But practically, let's say whether you are doing some electronics or something, so in the practical case, this will be a very high value. It's not a not is it's not infinity, which is not perfectly achievable here, of course. So it will be practically a very high value. Okay. So this is the Dirac delta function. So how we can represent this Dirac delta function? So you have something like this. A, so it just look at show a graph here. So this is your x and this is your fx, which is nothing but delta x minus a. I can represent, suppose this is x is equal to a. Everywhere in its locality also it is 0, but it spikes here at x is equal to a. Okay, this is a sudden spike here. So this means that it is tending to infinity. Okay, so this is your Dirac delta. So at x is equal to a, it is going towards or tending to infinity or a very high value, but all other cases it is remaining 0. In the practical case, you will not get the exactly same thing, but you will get something like this. So 0 and then it suddenly increases and it quickly just goes down again and becomes 0 again. Okay, so this is how you will get the in practical cases. Okay, so this is how the Dirac delta function looks like. So what are the features of the Dirac delta function? So the features of Dirac delta function, you can show it here only. So this is the height. This height will tend to infinity. As you can see, I'm telling that this function is tending to infinity. So its height, h is the height of this curve, or very, I will not say curve, this is a line I will say. Okay, so this arrow is tending to infinity, and width, on the other hand, is tending to 0. I will show you with a very good square function or a rectangular function and try to show that what is actually happening. I will show it later. But another important thing is that for Dirac delta is that if you take, say, minus infinity to infinity or 0 to infinity, it doesn't matter. Okay, you take delta x minus a dx, you will always get it equal to 1. That means what? What is the integration of a function means? Integration of a function means what? So suppose you have a function f of x and you are integrating it from here to here. That means what? It is the area under the curve, right? So area under the curve is represented by the integration f x dx from whatever x naught to x1, whatever. So wherever you are finding some integration, that means it is the area under the curve. So area under this curve, the area is this part is equal to always equal to 1. So area is always equal to 1. So this has to be remembered. Okay, the area should be always equal to 1. Okay, area under the curve is equal to 1. Okay, now some other things like in Dirac delta function, the area under the curve or under the Dirac delta curve is actually called the strength of the Dirac delta. Strength of the Dirac delta. Okay, so suppose you have f of x which is equal to 3 times delta x minus 3. Okay, what does that mean? Let us draw the curve and let's discuss it. Okay, so you have something like this. All right, so these are y axis, this is your x axis. This is your f of x, which has to be represented. This is your x. And this is suppose x is equal to 3. So what is this happening? What is here happening? Is that at x is equal to 3, it will spike. So actual function will be something like this. It is going, and it is coming back like this. Remember here, the strength of the direct delta is not 1 here. It is 3. Okay, this is the strength. Okay, once I'm telling that the strength of the direct delta should be always 1. Again, I'm telling that no, it is not always 1. It can be 3 also. Simple thing. I have only integrated delta x minus a. If I have to integrate 3 times delta x minus a, it will be 3. Okay, so this is what you will have. All right, so this is what you will get. So 3 into delta x minus 3. That's why whenever we are doing f of 0 into delta 0, we were just writing f of 0 in the Laplace transform wherever we were doing that. Okay. So this is what it is. So this is the strength or the area. So area under the curve here, it will be equal to 3. And so this is the strength or the area of direct delta dB I am writing right now. Okay. And at x is equal to 3, there is a sharp peak. So sharp peak at x is equal to 3. All other points, practical case, like what I have drawn here, not exactly equal to 0. So at 3 plus here, you will find that there is some value. But theoretically, it should be 0. So this is the concept. Okay. If I take another function, say f of x is equal to say minus 2 delta x minus 3, then how will you represent this? So for that, again you draw it, it doesn't matter. So you take this curve. So this is your again effect. This is x, and this is equal to 3. Again, you know that if x is equal to 3 only, it will be happening. So what you have to do is that you take this, and now this becomes something like this. Okay. Now it is minus 2. Remember, the area of the strength is minus 2. So the direction changes. Okay. But x is equal to 3. This remains same. The peak will be still at, or the peak, sharp peak, will be at x is equal to 3. But the function values will change. It will be in the negative values. So this is how the Dirac delta is represented in a graphical form. Okay, some more properties. Let me give you. Yeah, that is the word which I was talking about. That will help you to understand. So let us take a rectangular function first, and then we will see that how we can approach towards a Dirac delta function. Okay, so you have a positive quadrant of x and y, or f of x, you can say, and you have a function like this. So this is at x is equal to a. This is a minus some sigma. This is a plus sigma. So you can see that this is a, and this is plus sigma. This is minus sigma. So it is a 2 sigma width, right? This is a 2 sigma width. Alright, this you can see a plus sigma minus a minus sigma. So it's a 2 sigma width. What is the height of the function? This is 1 upon 2 sigma. So how we can represent this function? F of x, which is equal to 1 upon 2 sigma from a minus sigma from x to a plus sigma. And all other points it is 0. Alright, this is the function. Now, how we can go towards the Dirac delta? Okay, what will be the area of this function? This. So what is the width? Width is 2 sigma. What is the height? 1 upon 2 sigma as per the function given. So what is the area? Area is 1. Very interesting. Area is 1. So now what we are doing is that area is 1 we have seen. So at x is equal to a, what we are doing is that now we will, the width I will reduce. If I reduce the width, if I have to keep the area equals to 1, what I have to do? The height has to be increased like this. Area here will be equal to 1 also. area here is also equal to 1. Further, if you go, it will be also equal to 1. So you can see that what is happening is that, so finally you get something like this, which is also having area equals 1. But for this case, you have area equals 1, no doubt. Width will be tending to 0 and height is tending to infinity. This is what you call as the Dirac delta function. Okay, so from a rectangular function we have tried, and then we just squeeze the width and increase the height to keep the area same. Okay, and this is how we approach towards the Dirac delta. Okay, so this is one of the things. Now, there is a property here. Let me just show that if a function is discontinuous, discontinuous at some point, its first order derivative will be a Dirac delta function. Okay, so how we can prove it? So f of x is equal to 0, suppose at x less than a, and it is equal to some c at x greater than, yeah, it's okay. Okay, so how we can represent this? Very easy. So you have this point where it is suddenly getting a jump and it remains like this. Okay, and here it is 0. So here your f of x is equal to 0. Here your f of x is equal to 3, and it is continuing. Remember, it is continuing. Okay, and this point is x equals a, where it is giving a sudden transition, and this value is. All right. Now, what we do is that we first have to check where is our positive x direction. So this is our positive x direction, right? So what we'll do is that we'll move in this direction, in the direction of the positive x, and try to see what will be the derivative at different places. Let's take this point. What is the derivative here? So for the derivative, what you have to do? Change in function to that of the small change in x. Okay, fine. At this point, let's say this point is A. So at point A, df dx for a small change in x, is there any change in the function? No, it remains 0. So df remains 0 at even in a small change in x. So it is 0. Great. So at point B, I will show this is the point suppose B. Okay. So at point B, is it changing? No. The function remains same c minus c by some delta x, which is 0. Clear? What about at x is equal to small a? This point, which is let's say represented by some y. So at point y or x is equal to a with a small change in x, okay, with a very small change in x, what is happening? It is becoming c minus 0 divided by some delta x, which is very small, no doubt. This delta x, I'm saying that is tending to 0. When I do this, it is tending to infinity, right? If I just squeeze the delta x limit and there is a finite value over here, then this will tend to infinity. And this is what we are calling as the Dirac delta function. So df dx will be some sort of a Dirac delta function with discontinuity as the strength. This is the strength of the Dirac delta. Okay, this is the thing which needs to be kept in mind. All right. So whatever the discontinuity is there, add that point, at the point of discontinuity, the derivative of the function becomes a Dirac delta function with the strength or the area of the Dirac delta equal to the amount of discontinuity. So the amount of discontinuity is C here. Okay, why not it is minus C? Because you have to go in the positive x direction to see that. Okay, so here it is 0. In the positive x, it is becoming positive C. Okay, but if this is the positive x direction, let's say, then here it is 0 and here it is C, so it will be minus C. So remember, so in the positive x direction, the amount of discontinuity is the strength of the derivative. Okay, I think this is enough for uh, understanding the Dirac delta function. We will not solve much questions over that. We'll just calculate the last couple of things. That is, first is the properties. Let us talk about some properties of Dirac delta. Where everything you don't need to remember, just some properties are important. Dirac delta function. Number one is that this is important. Minus infinity to infinity or 0 to infinity, whatever. F of x delta x minus a dx. So this is the thing you get the answer as f of e. Okay, because you know that x is equal to a only there is something. So that will come in the function and that will be the result. Number two, minus infinity to infinity. If dash x, if the derivative of the function is being multiplied with x minus a, Dirac delta, it becomes minus f dash a. Okay, these two are important. Otherwise, this is also you can say that x minus a. See, delta of c times x minus a is 1 upon mod c delta x minus a. Okay, these are not important. These are not required for you. So this is minus infinity to infinity delta x minus a and delta x minus b dx is equal to delta a minus b. And that's all. These are the four properties. This is the most important. This is fine. You don't require this actually. Fine. Let's go ahead further. And let's calculate the Laplace transform of the Dirac delta and the Fourier transform of the Dirac delta. Both we have seen how to calculate the Fourier transform and the Laplace transform. And not much difference is also there. So we can do that. Okay. So first is the Laplace transform of Dirac delta. Okay. So the Laplace transform of Dirac delta. So what is the function? F of x, which is nothing but delta x minus a. Okay. This is not now. Delta x minus a means x is equal to 8 will be infinity and otherwise it will be 0. Now what I do? Laplace transform definition. So A log f of x. This is delta x minus a e to the power minus s x dx. This is the Laplace transform definition. You've seen it so many times. Apply the property of the Dirac delta function. See, minus infinity to infinity fx delta x minus a dx is f of a. It doesn't matter whether it starts from minus infinity to infinity. You can also apply it from 0 to infinity because delta x minus a is at a particular value only where it will satisfy. Okay, so and we are assuming that in case of Laplace transform, it is a positive value where that is any is positive, some positive value. So what it will be therefore minus e to the power minus s times. That's all. This is the Laplace transform of the Dirac delta function. Very simple. Similarly, the Fourier transform of Dirac delta. So what is that? Fourier transform, we know it is minus infinity to infinity. You can put root 2 by pi or something, that's not important. F of x e to the power minus iota s x dx. This is the Fourier transform definition. So the Dirac delta minus infinity to infinity, you have what is that? Delta x minus a e to the power minus iota s x dx. So finally we will get e to the power minus iota s e. Okay. Along with that, you can put 1 upon root 2 pi or root 2 by pi, whatever it is. Okay. So this you can also put. Fine. So these are how you calculate the Dirac delta functions, Laplace transform and Fourier transform. So these are a couple of things which one must know. Okay. Now maybe we have some half an hour or 25 minutes. I think we can go for the Green's function. Before moving into the Green's function, uh, fine, let us go there. Actually, okay. The next part will be the Green's function and how do we calculate the or solve the ordinary differential equation, particularly the particular solution using the Green's function. That is what we will try to see. Okay. In detail, if you have to go, then go to the lecture notes. I will just give a mathematical formulation or mathematical, I would say, what the algorithm to solve the differential equations. So it might not match with the problems which are being discussed. It is somewhat different, but ultimately giving the same result. Okay, just a minute. Okay, this is all about the Dirac delta. So Green's function using green color. So fine. So the first thing is that if you have say some kind of a differential equation, let me just show you it, the example which is given in the week 8 content only. So let's start with that. Okay, so you have suppose an equation like this d2x dt2 plus omega square x is equal to f of t, and it is given that x of 0 is 0 and x dash of 0 is also equal to 0. So remember, this is applied only when this kind of initial value problem is there or initial conditions are there. This sometimes are called as the homogeneous initial conditions, where x of 0 is 0, x dash of 0 is also 0. So this condition is very important for solving using this particular technique. Okay, so you have a forcing function here. So this clearly tells you that it is the inhomogeneous differential equation with order t. Fine. Now, what I do is that if I write f of t as 0 to infinity, f of some dummy variable t dash, anything, any variable, you can write some u also. Okay, t dash delta t dash minus t dt dash. Can we write this as f of t? Yes. Why? Because we have just now seen the property of the Dirac delta that if you take a 0 to infinity and just see that t dash is equal to t, you just have to put it here. That will be nothing but f of t. So this is fine. This we can write. Okay. Now, what we do is that let me first write and then tell you. So d2 by dt2, you will find entire these mathematical things which I am writing in the week 8 content. You can go ahead with more details. So g of t comma t dash, okay, is plus omega square. So what is this g? That is the question. So we will see that very soon. This will be equal to delta t dash minus t. Whoa, well, so in the right hand side, we were having first f of t I'm writing now this as some impulse function or Dirac delta function. So this thing, this, so I would say that the solution to a problem where forcing function, that is the FT forcing function, is replaced. Because that is what we have done. F of t is being now replaced with a Dirac delta. So replaced, and that is what we are calling as your impulse function. Replaced by an impulse function. The solution to this problem is called or is the Green's function. That's why we have written it as g of t or something, right? T comma t dash. So what it is done here from this step to this step, the one thing which is being done is there. In the right hand side, the forcing function has been replaced by only a Dirac delta function. Corresponding changes are reflected in the x. That corresponding change and its solution is the Green's function. So how do we define it? The x of t. So x of t can be written as 0 to infinity g Green's function t comma t dash f of t dash dt dash. This is how the x of t is defined. Now, if you just put this integral over here, and see that what will be the thing, you will actually get original equation this. Okay. So what I am trying to say is that look at this equation. You multiply each of these equation with f of t dash. Okay. And then integrate between from 0 to infinity and all these things. You will find out that this is x, this is also x because as per the definition, and this becomes f of t, the original equation. So some kind of manipulation we are doing such that the force function becomes equal to the Dirac delta function. So we are replacing, and we are saying that we are replacing with some Green's function, and the solution to this particular problem is the Green's function, or can be defined like this. Okay, so this is what we are essentially doing. Fine, we will see some questions definitely, and now based on this part, we will try to solve for the Green's function and hence x. So what it will be d2 by dt2 g of t comma t dash plus omega square g of t comma t dash is equal to delta t dash minus t, right? This is what you will be having. Now what I do is that for solving the ODE, we have just now used the Laplace transform, right? So apply Laplace transform. That's the best thing. You apply Laplace transform, what you will get? This is s square g of s. And if you write now y dash of 0 and y of 0, this will be 0. All are 0, right? The initial conditions, x of 0 or x dash of 0. So we are writing that g of that are also 0. Okay? Plus omega square g of s. And on the other hand, we have seen that the Laplace transform of this will be minus s t. We have just now found out. Minus s e. So here, the variable is t dash, value is t. So that's why it is. All right. So now what will be the GS? The G of S will be equal to e to the power minus st divided by s square plus omega square. Well, of course, there will be some kind of a sine function, but e to the power minus st divided by something if it is there, and if you have to take its inverse Laplace transform, then it will be somewhat kind of a unitary function. So its solution generally will be 0 when t is less than t dash and 1 upon omega. This is, sine of omega t dash minus t, or is it okay? T minus t dash maybe. Okay. So when t is greater than t, something like this, you will get. Okay. So the thing is that this this one is nothing but some kind of a unitary function kind of thing. You can look into the last lecture what I have provided. You can see about the unitary function or search in the internet about the unitary function and try to see how the Laplace transform is being calculated. So based on that, actually it is being written. And finally, your x of t is 0 to t 1 by omega sine of omega t minus t dash. Okay, f of t dash d dash. Okay, so this is will be the final answer. So I have seen a couple of questions in the assignment which is based on this. So you just have to think about that. I think these are very simple questions in the assignment which are given. So just if you just look at the week 8 content and try to read at least once, you will be able to solve it very easily. So you don't need to understand each and every thing. Just focus on these parts and you will be able to get the results. Okay. Now, I have seen that using Green's function, there are some questions to solve the ordinary differential equation in the assignment. So I want to solve some questions and give you some insight about how to solve a general ordinary differential equations using the Green's function. Okay, so that's what I will show, and we will end up the class based on that. Okay, so there are two things. Okay, for solving questions, I would recommend you to use this method, but it's your own choice. Okay, so for solving questions, this is I find it easier, so that's why I will show it to you. So you first define Green's function. Okay, define Green's function, that is g of instead of t and t dash, I'm writing x and t. Okay, don't confuse it between space and time. It is some x and t, some two variables. So you write it y1 of t, y2 of x. Let me write and then I will explain what is happening. Y1 of x, y2 of t divided by w of this w of t is what we have seen earlier is the Ron's scale. Okay, how it is defined is simple. Y1 of t, y2 of t, y1 dash of t, y2 dash of t. That means first order derivative. Okay, now what we will do is that we say that for, okay, let me just write the particular solution yp, particular solution of the ODE, because complementary solution you know how to calculate. Now, for yp of x, it is actually some zero or some x naught, I would say, the initial condition to some x, g of xt, which is being calculated using this, okay, f of t dt. Now, what is this f of t? Question arises, what is this f of t? So, f of t is the forcing function of the ODE. Okay, now I will now explain what is actually happening, what I am trying to say, and I will explain it using two questions. One is the first question is, let us say y double dash minus y dash is equal to 1. Remember, the initial conditions should be like this: y of 0 is equal to 0, y dash of 0 is also equal to 0. Okay, this kind of initial condition is very important. First, step 1 is that as we do for general inhomogeneous or non or homogeneous equation, find the complementary solution. Okay, find the complementary solution. So what you will get is that alpha squared minus alpha is equal to 0 because this is the inhomogeneous part. This is the forcing part, which is a constant function in this case. But yeah, we will look at for the homogeneous equation. So alpha into alpha minus 1 is equal to 0. So either alpha is 0 or alpha is equal to 1. Similarly, so the y complementary function will be e to the power 0 or e to the power x. So it is C2, which is C1. Now, we will not write this as some constant and we will try to check. So y1, we define it as e to the power 0, which is equal to 1 this way. And y2, we define it as e to the power x. Fine. This is now been defined. Now can we calculate? The second step is calculate green function. Green's function. Okay. So what it will be? G of x comma t. Let me write it down. Y1 of t, y2 of x minus y1 of x, y2 of t divided by the Wronskian WT. Okay. Okay. So y1, y2 we know. W of t is what we need to calculate. So what is that? Y1 of t is what? 1. Y2 of t, e to the power t. It is actually e to the power x, but we are writing it in terms of a dummy variable t. Okay. Next, y2 of, I'm sorry, something, okay, the differentiation of this. Differentiation of this is 0. What about it? This e2. So, take the determinant, it will be e to the power. Done. Wt is calculated. Then what is g of xt finally? Is y1 of t. What is y1 of t? Y1 of t, we have found out 1. What is y2 of x? E to the power x minus. What is this? 1. And what is y2 of t? E to the power t. Divided by e to the power t. Okay, this is fine. So you get therefore e to the power x minus e to the power t divided by e to the power t, or e to the power x minus t minus e to the power t minus t, or e to the power x minus t minus e to the power 0 is 1. So this is your Green's function which is being calculated. Okay. So this is one of the things which is being calculated. Now, next part is third part, calculate YP. And I have already told you what is the YP's definition, as we have seen earlier also when I was doing the mathematical part also. Yes, see, not this one, uh, this one. See, Green's function times the function times the sorry, with respect to what it is being integrated. Okay, so it will be some 0 to x because x at 0 is 0. So, sorry, y at 0 is 0. So, the zeroth value we are giving up to x. So, e to the power x minus t minus 1 into f of t is 1, right? This is 1 dx. So, solving this solving is easy. You can do it very easily. Okay, so 0 to x, e to the power x, e to the power minus t dx. Okay, minus dx from 0 to x. I'm sorry, this should not be dx. It should be the dummy variable dt. Sorry. Okay, it's fine. Dt, d2. Let me check whether I have dt. Yeah, dt. Yes. Okay. So next will be e to the power x. We are integrating with respect to t. So this will be integrated. So it will be e to the power minus t with a minus sign, 0 to x minus. This will be t from 0 to x. So what it will be now? Minus e to the power x, e to the power minus x, minus minus will be plus e to the power x, e to the power minus 0, minus x minus 0. That's all. So you get minus 1, this is 1, right? E to the power 0 is 1, so e to the power x minus x. This should be the particular solution. Okay, so this is your y. And the final solution will be y complement plus y. That's all. All right. So this is what your the way to calculate the particular solution using Green's function. So this is the step you should follow. That's all. I will solve another question and then we'll end today's this particular lecture. Okay. One more question I will give, which consists of everything, means two, three terms. So it will be easy for you to understand. So this is the differential equation y double dash minus 4y dash. So all the derivatives are present here. 3y is equal to 2 e to the power 2x. And again, the conditions are y of 0 is 0, y dash of 0 is 0. Okay. So first step, what I have told, to calculate the complementary function. And complementary function can be calculated using auxiliary equations. Okay, and so alpha square minus 4 alpha plus 3 is equal to 0. So alpha will be what? 4 plus minus root over b square. 16 minus 4 3 is 12 divided by 2. So alpha is equal to 4 plus minus 2 divided by 2. So it will be 4 plus 2 6 or 4 minus 2 2. So it will be 2 by 2 1 and 4 plus 2 6 by 2 is 3. So alpha is 1 and 3. Therefore, y will be equal to c1 e to the power x plus c2 e to the power 3x. So I will write y1 is equal to e to the power x and y2 is equal to e to the power 3x. Second step, calculate Green's function. Okay, calculate Green's function. But before calculating the Green's function, you have to calculate the Wronskian, which will be in terms of a dummy variable t. So you have e to the power t, e to the power 3t, differentiated e to the power 3, e to the power t, differentiate this 3 e to the power 3. Do the determinant, so it will be 3 e to the power 4t minus, I'm sorry, something, oh, no, that is okay, this is fine, e to the power 4t. Right. So I thought it will be 0, no, there is a 3 here. So it will be 2 e to the power 4t. This is the Wronskian which we have got in terms of the dummy variable. Okay. Now, what is the Green's function? G of x comma t. So what it is? Y of y1 of t, that is e to the power t, y2 of x e to the power 3x minus y1 of x e to the power x, and this is e to the power 3 divided by the Wronskian through e to the power 4t. So can we do some more stuffs like half e to the power minus t e to the power 3x minus half e to the power x e to the power minus t. Just solving this. Okay, so g of xt, the Green's function, is ready. Now the only part is third part, which is calculate y. All right, so let's do the yp. This is, so it will be 0 to x g of x comma t ft dt. Okay, so once you do this, let's solve this integration and stop for today. So 0 to x, this is half e to the power minus 3t e to the power 3x minus e to the power x divided by 2 e to the power minus t times 2 e to the power, I think, 4t, right? No, no, just a minute. Forcing function. 2 e to the power 2x. Okay, so just write it here. F of x is 2 e to the power 2x, the forcing one. So f of t will be 2t. All right, so this 2, 2, and this 2 cancels. Now just you have to solve the integration, that's all. So one integration will be e to the power, let's okay, minus pt. This e to the power 2t if I multiply, it becomes 2t e to the power 3x minus e to the power x e to the power minus t e to the power 2t dt. Fine. Let's go to the next step. 0 to x e to the power minus t e to the power 3x e to the power x e to the power minus t dt. Now separately solve the integration. That's all. E to the power 3x. This is not going to be integrated because it is in terms of x. Only this will be integrated. Minus t with a minus sign. 0 to x minus e to the power x, and this will be also minus sign e to the power minus from 0 to. So finally, minus e to the power 3x e to the power minus x, okay, minus minus becomes plus e to the power 3x e to the power minus 0 plus e to the power x e to the power minus x minus e to the power 0 sorry, x e to the power minus 0. So what finally we are getting? Minus e to the power 2x plus e to the power 3x plus 1 because it will be e to the power 0 e to the power x. Okay, something I might be missing somewhere. I think somewhere I have done something wrong. I think here I have done something. Something is not right. Oh yeah, 2t is minus, and hence this will be negative. This will not change much. Sorry, this is minus is fine. This is 0, and this will be plus. Okay, with a negative sign. This will be plus. I think this is fine now. So minus e to the power 2x, fine, e to the power 3x minus e to the power 2x plus e to the power x. So what we are getting, minus 2 e to the power 2x, this and this, plus e to the power 3x plus e to the power x. So this is the solution. Okay. So with this, I think we can stop for today. So we have already discussed about the Green's function. To solve the ODEs, we have discussed enough about the direct delta function, which is important for the Green's function and other things. Then the previous whatever was left about, like the inverse Laplace transform and using the Laplace transform to solve the ordinary differential equation, that we have seen. Okay, so we can stop here. Thank you.